Welcome! Today, we'll tackle LeetCode problem number 922, titled Sort Array by Parity 2. This problem challenges us to rearrange an array so that even-indexed positions hold even numbers and odd-indexed positions hold odd numbers. Let's dive in and explore efficient solutions to this interesting problem. In this problem, you are given an array of integers called nums, where the length of the array, n, is always even. The array is structured in a way that exactly half of the elements are even numbers and the other half are odd numbers. Your task is to rearrange the elements so that all even numbers are placed at even-indexed positions, which are indices like 0, 2, 4, and so on, and all odd numbers are placed at odd-indexed positions, such as 1, 3, 5, and so on. The final output should be an array that satisfies this condition, and you can return any valid arrangement that meets these requirements. The input will be the array nums, and the output should also be an array of the same length, but rearranged to meet the parity condition. Let's look at an example to understand the requirements better. Suppose we are given the input nums equals 4, 2, 5, 7. In this case, one valid output is 4, 5, 2, 7. Here's why: the number 4 is even and is placed at index 0, which is an even index. Similarly, the number 5 is odd and is placed at index 1, which is an odd index. Continuing this pattern, 2, which is even, is placed at index 2, and 7, which is odd, is placed at index 3. This arrangement satisfies the condition where numbers at even indices are even, and numbers at odd indices are odd. This is just one possible solution, as there could be other valid outputs with the same properties. Now, let's consider another example where nums equals 2, 3. In this case, the output is 2, 3. Here, 2 is even and is placed at index 0, and 3 is odd and is placed at index 1. Since the array only has two elements, this is the only valid arrangement that satisfies the parity condition. For cases with more elements, there are often multiple valid outputs. For instance, with the earlier example of nums equals 4, 2, 5, 7, other valid outputs could include 2, 5, 4, 7, or 4, 7, 2, 5. As long as even-indexed positions contain even numbers and odd-indexed positions contain odd numbers, the solution is acceptable. Let's examine another example with a slightly larger input, nums equals 1, 2, 3, 4. One valid output here is 2, 1, 4, 3. In this output, the even numbers 2 and 4 are placed at indices 0 and 2, which are even indices, while the odd numbers 1 and 3 are placed at indices 1 and 3, which are odd indices. This arrangement satisfies the problem's requirements. The constraints for this problem specify that the length of the array, n, will always be an even number between 2 and 20,000. Additionally, all elements in the array will be integers between 1 and 1,000. These constraints ensure that it is always possible to find a valid solution for any input that meets the given criteria. There are a few important edge cases to consider. For the smallest possible input size, where n equals 2, such as nums equals 2, 3, there is only one valid output. Another scenario involves handling arrays with both the smallest and largest values within the range, such as nums equals 1, 1000, 3, 998. Additionally, if the input array is already sorted by parity, for example, nums equals 2, 1, 4, 3, you can simply return the same array as the output. On the other hand, if the input is completely unsorted, the solution must still rearrange the elements to meet the parity condition. It's worth noting that the problem guarantees the existence of a solution because the input always contains an equal number of even and odd integers. This means you can focus on finding any valid arrangement without worrying about edge cases where a solution might not exist. To solve the problem of sorting an array by parity such that even-indexed positions contain even numbers and odd-indexed positions contain odd numbers, we first need to consider the constraints. Since the input guarantees exactly half of the numbers are even and the other half are odd, we know a valid solution is always possible. One straightforward way to approach this is through a brute force method. Here, we pass through the array twice, once to collect all the even numbers into a separate list and once for the odd numbers. After that, we construct the result array by alternating between these two collections. While this method is simple and intuitive, it does require additional space to store the two separate lists. The overall time complexity is O(n), as we traverse the array twice, and the space complexity is also O(n), due to the auxiliary lists. While this approach is easy to implement, it has the downside of not being memory efficient, particularly for larger arrays where minimizing space usage is critical. A more efficient option is the two-pointers approach, which eliminates the need for extra space by rearranging the array in place. The idea here is to use two pointers, one for even indices and one for odd indices, and resolve mismatches through swapping. For instance, if we find an odd number at an even index, we look for an even number at the current odd pointer and swap the two. This approach leverages the constraint that the array contains an equal number of even and odd numbers, ensuring that mismatches can always be resolved through swaps. By incrementing the pointers appropriately after each operation, we ensure that the entire array is processed efficiently. This strategy allows us to achieve the same O(n) time complexity as the brute force method, but with an impressive O(1) space complexity, as no additional data structures are required. The two-pointers method is highly efficient, with a time complexity of O(n), since each index is visited only once, and a space complexity of O(1), because it operates entirely in place. This means we avoid the overhead of creating auxiliary lists or queues, making it an excellent choice for optimizing memory usage. However, the implementation is slightly more complex than the brute force method, as it involves careful management of the pointers and swaps. Another alternative to consider is the two queues approach. This method is conceptually similar to the brute force approach, but instead uses queues to manage misplaced even and odd numbers. Once the mismatches are identified in the first iteration, the queues are used to replace values in the second pass. While this method also has an O(n) time complexity, it requires O(n) space for the queues, making it less efficient in terms of memory compared to the two-pointers approach. When comparing these methods, the two-pointers approach stands out as the optimal solution. Its in-place operation eliminates the need for additional memory, which is particularly advantageous for large input sizes. While the brute force and two queues methods are easier to implement, they come with the trade-off of higher space complexity. The two-pointers approach strikes the right balance between performance and memory efficiency. It achieves optimal time complexity of O(n), while maintaining O(1) space complexity, making it scalable and suitable for handling large datasets. Additionally, the guarantee of an equal number of even and odd numbers ensures that mismatches can always be resolved, lending robustness to this strategy. Despite its slightly more complex implementation, the performance benefits far outweigh the added complexity, solidifying it as the preferred solution for this problem. To summarize, the brute force method is straightforward but requires extra space due to the separate lists for even and odd numbers. The two queues method offers similar time complexity but is less space efficient compared to the two-pointers approach. The two-pointers method, while slightly more intricate to implement, ultimately provides the best combination of performance and memory usage. It is efficient, scalable, and highly memory optimized, making it the ideal solution for this problem. However, due to its in-place nature, it may require careful debugging to ensure pointer operations are managed correctly. Overall, the two-pointers approach is the most practical choice, offering an excellent balance of simplicity and efficiency for sorting the array by parity. To solve problem number 922, sort array by parity 2, we need to rearrange the given array so that every even indexed position contains an even number, and every odd indexed position contains an odd number. We start by validating the input to ensure the array has an even number of elements, as guaranteed by the problem. Next, we initialize two pointers, one called even_idx, starting at index 0, which will track the even positions, and another called odd_idx, starting at index 1, which will track the odd positions. These two pointers will traverse the array, ensuring elements are placed in their correct positions. The algorithm proceeds by iterating through the array, ensuring that both pointers stay within bounds. This setup is the foundation for the swapping and placement logic that follows. The core of the algorithm lies in checking the values at the current pointer positions and swapping elements if necessary. If the value at even_idx is already an even number, it's in the correct place, so we simply increment even_idx by 2 to move to the next even index. Similarly, if the value at odd_idx is already odd, we increment odd_idx by 2 to move to the next odd index. However, if we find that the value at even_idx is odd and the value at odd_idx is even, these two elements are swapped to correct their positions. After swapping, both pointers are incremented by 2. This process continues until all elements are processed, meaning both pointers go out of bounds. Once the loop completes, the array is guaranteed to be sorted by parity, and we return the modified array as the result. There are a few key insights that make this algorithm particularly efficient. First, the use of 2 pointers allows us to traverse the array in a single pass, focusing specifically on even and odd indices. This eliminates unnecessary checks and ensures that each element is handled only once. Second, our swapping strategy modifies the input array directly, avoiding the need to create a new array. This in-place modification keeps the space complexity at 1. Additionally, the problem guarantees an equal number of even and odd integers, so we don't need to handle edge cases where the array might be invalid. Finally, the algorithm's single-pass approach ensures a time complexity of n, making it highly efficient for large input sizes. The algorithm relies on 2 simple data structures. First, we have the input array nums, which is modified in place as we rearrange its elements. This avoids the overhead of creating additional memory for a new array. Second, we use 2 pointers, even_idx and odd_idx. The even_idx pointer tracks the current position in the array where an even number should be placed, while odd_idx tracks the position where an odd number should go. These pointers move independently, jumping by 2 positions each time, ensuring that they only process the indices relevant to their respective roles. This straightforward approach keeps the implementation clean and efficient. Let's walk through an example to see the algorithm in action. Consider the input array nums equals 4, 2, 5, 7. Initially, even_idx starts at 0, and odd_idx starts at 1. At the first step, nums, even_idx, is 4, which is even, so we simply increment even_idx to 2. Next, we check nums, odd_idx, which is 2. Since 2 is even, it's in the wrong position for an odd index. We swap nums, even_idx, which is 5, with nums, odd_idx, which is 2. The array now looks like 4, 5, 2, 7. Both pointers are increment, even_idx becomes 4, and odd_idx becomes 3. Finally, we check nums, odd_idx, which is 7. Since 7 is odd, it's in the correct position, so we increment odd_idx to 5. At this point, both pointers are out of bounds, and the process ends. The final output is 4, 5, 2, 7, which satisfies the problem's requirements. Now let's analyze the complexity of the algorithm. The time complexity is n, because we traverse the array once, performing constant time operations such as checks and swaps at each step. This ensures the algorithm is highly efficient. The space complexity is 1, since the operations are performed in place, and no additional memory is allocated for another data structure. By combining in-place modifications with the 2-pointer technique, we achieve an optimal balance of time and space efficiency, making this solution well-suited for large inputs. The solution begins by defining a class solution and a method sortArray by parity II that takes the input nums. The problem guarantees that the input array always contains an equal number of even and odd integers. We first determine the length of the input array nums and initialize 2 pointers, even_index starting at 0 and odd_index starting at 1. These pointers help track where the next even and odd numbers should be placed in the result array. We also create a result list of the same size as nums, initialized with zeros, to hold the rearranged values. The method then iterates through each number in nums. If the number is even, determined by checking number %2 == 0, it is placed at the current even_index in the result array, and even_index is incremented by 2 to point to the next available even position. Similarly, if the number is odd, it is placed at the current odd_index, and odd_index is incremented by 2 to point to the next available odd position. This ensures that all even numbers are placed at even indices and all odd numbers at odd indices. The method completes by returning the result array, which is the desired output. This solution runs in n time, as it processes each number in the array exactly once, and uses n additional space for the result array. The implementation is simple, efficient, and adheres to the problem's constraints. This is the Java implementation of LeetCode problem number 922, sortArray by Parity 2. The logic mirrors the provided Python implementation, with adjustments for Java's type declarations and syntax. Key differences include the use of explicit data types such as int and the enhanced for loop for iterating through the array. The method returns a new array where even indexed positions contain even numbers and odd indexed positions contain odd numbers. To solve the problem, we begin with the input array nums, which in this example is 4, 2, 5, 7. First, we initialize several variables. The length of the array, n, is 4. We use two pointers, even_index, starting at 0, to track positions where even numbers will be placed, and odd_index, starting at 1, to track positions for odd numbers. We also create a result array of size n, initialized to all zeros, 0, 0, 0, 0. Now, we iterate through each element in nums. The first number is 4, which is even because 4% 2 equals 0. So, we place 4 at the position indicated by even_index, which is result, 0. This updates the result array to 4, 0, 0, 0. Then, we increment even_index by 2 to point to the next even position, making even_index equal to 2. Next, we encounter the number 2, which is also even. We place it at result, even_index, updating the array to 4, 0, 2, 0. Again, we increment even_index by 2, so it now equals 4. Now we move to the third number, 5. This number is odd because 5% 2 is not equal to 0. We place 5 at result, odd_index, which is position 1, updating the result array to 4, 5, 2, 0. Then, we increment odd_index by 2, so it becomes 3. Finally, we process the fourth number, 7, which is also odd. We place 7 at result, odd_index, updating the result array to 4, 5, 2, 7. Once again, we increment odd_index by 2, making it equal to 5. At this point, we've traversed all the numbers in the input array, and the final result array is 4, 5, 2, 7. This array alternates even and odd numbers at even and odd indices, respectively, which satisfies the problem requirements. Let's look at another example where nums is 3, 1, 4, 2. Like before, we initialize the key variables. The length of the array, n, is 4. We start with even_index at 0 and odd_index at 1, and the result array is initialized to 0, 0, 0, 0. Now, we iterate through the array nums. The first number is 3, which is odd since 3% 2 is not equal to 0. We place 3 at result, odd_index, which is position 1, updating the result array to 0, 3, 0, 0. We then increment odd_index by 2, so it becomes 3. The next number is 1. This is also odd, so we place it at result, odd_index, which is position 3. The result array is updated to 0, 3, 0, 1, and odd_index is increment by 2 again, making it 5. Next, we process the third number in the array, which is 4. This number is even because 4% 2 equals 0. We place 4 at result, even_index, which is position 0, updating the result array to 4, 3, 0, 1. Then, we increment even_index by 2, so it becomes 2. Finally, we process the last number in the array, which is 2. Since 2 is even, we place it at result, even_index, which is position 2. This updates the result array to 4, 3, 2, 1. We increment even_index by 2, making it 4. At this point, all numbers in nums have been placed, and the final result array is 4, 3, 2, 1. This array successfully alternates even and odd numbers at the correct indices. For our third example, we start with nums as 2, 3, 6, 5. As before, we initialize the variables. The length, n, is 4. We set even_index to 0 and odd_index to 1, and the result array starts as 0, 0, 0, 0. Now, we process each number in nums. The first number is 2, which is even since 2% 2 equals 0. We place 2 at result, even_index, which is position 0, updating the result array to 2, 0, 0, 0. We then increment even_index by 2, so it becomes 2. The next number is 3. Since 3 is odd, we place it at result, odd_index, which is position 1. This updates the result array to 2, 3, 0, 0, and we increment odd_index by 2, making it 3. Next, we handle the third number, 6. This number is even because 6% 2 equals 0. We place it at result, even_index, which is position 2. The result array is updated to 2, 3, 6, 0. We then increment even_index by 2, so it becomes 4. Finally, the last number in the array is 5, which is odd. We place it at result, odd_index, which is position 3. This updates the result array to 2, 3, 6, 5, and odd_index is increment by 2, making it 5. At this stage, all numbers from nums have been placed correctly, and the final result array is 2, 3, 6, 5. This array alternates even and odd numbers at the correct indices, meeting the problem's requirements. In this solution, we process the input list nums in a single pass, ensuring efficiency. Let's break down the time complexity step by step. First, the initialization steps are straightforward. Calculating the length of the array n with len, nums, takes constant time, O1. Initializing the two pointers, even_index and odd_index, also takes O1. Allocating the result array, however, requires O(n) time because we are creating a new array of the same size as the input. Next, during the iteration phase, the for loop runs exactly once for each element in nums, meaning it executes n iterations. Within this loop, we perform operations like computing the modulus of a number with number %2, assigning values to the result array, and incrementing the pointers. Each of these operations is constant time, O1. Since the loop runs n times, these constant time operations add up to O(n). When we combine all these steps, the loop dominates the overall time complexity, making the solution O(n). The final time complexity of this solution is O(n), where n is the size of the input array. Now, let's analyze the space complexity. The input array nums is read-only, so it doesn't contribute additional space usage beyond the input itself, which is O(1). The result array, however, is newly allocated with a size of n, contributing O(n) to the space complexity. Additionally, we use a small number of variables, such as n, even_index, and odd_index, each of which takes constant space, O1. When we add these together, the dominant term is the result array, which requires O(n) space. Therefore, the total space complexity of the solution is O(n). This means the space usage scales linearly with the size of the input array. Let's compare this approach to a brute force solution. In a naive method, you might first separate the even and odd numbers into two separate lists, then merge them alternately into the output array. While this also takes O(n) time and O(n) space, it involves additional overhead for managing multiple intermediate lists and performing the merging step. In contrast, the current solution avoids these inefficiencies by directly placing numbers into their correct positions in a single pass, making it more streamlined and optimal. Additionally, when analyzing the best, average, and worst cases, the time and space complexities remain consistent at O(n). For example, even if all even numbers are already at even indices and odd numbers at odd indices, the algorithm still processes each element, leading to O(n) time. Similarly, in a random arrangement where the worst-case scenario where all even numbers are misplaced, the algorithm still iterates through the input once, maintaining O(n) time complexity. To mathematically verify the big O complexity, consider that the algorithm performs constant time operations, O1, for each of the n elements in the input array. The initialization phase includes creating the result array, which takes O(n), and computing n, which is O1. These steps combine to O(n). During the iteration, the loop executes n iterations, and each iteration involves constant time operations like modulus calculation, assignment, and pointer updates. This results in O(n) for the loop. When summing up these contributions, the total time complexity is clearly O(n). For space complexity, the dominant term is the result array of size n, leading to O(n) space usage. No additional data structures of significant size are used. Therefore, both the time and space complexities of this solution are optimal at O(n), making it efficient for this problem. When solving this problem, there are a few common mistakes to watch out for. First, not validating the input constraints can lead to unexpected behavior. For example, if the array length isn't even or if the input contains non-integer values, your solution might fail or behave unpredictably. While constraints are typically guaranteed in competitive programming, it's always a good habit to test edge cases during development. Next, many people mistakenly use additional space, like creating separate arrays to store even and odd numbers. While this approach can work, it often violates the in-place constraint required in many interview settings. Instead, using a two-pointer technique is more efficient and adheres to O1 space. Another frequent issue is incorrect index management, confusing even-indexed and odd-indexed positions, or swapping elements based on their values instead of their indices. This problem is about aligning indices to their correct parity, so always double-check that part. Finally, avoid brute force solutions that iterate unnecessarily through the array multiple times, as this leads to O(n) superscript 2 complexity. Instead, aim for a more optimal solution that processes the entire array in a single pass, achieving O(n) time complexity. Handling duplicate numbers is another area where mistakes are common. Algorithms that rely on the uniqueness of values can fail because duplicates might still need to be swapped for proper alignment. For this problem, your focus should always be on parity alignment, not on whether values are unique. From an interview perspective, this problem is a great chance to show your ability to understand and handle constraints efficiently. For example, interviewers may test whether you can process the input in O(n) time while also maintaining O(1) space. Be ready to explain trade-offs in your approach, such as why you avoided extra space or how your solution ensures in-place modifications. The two-pointer technique is particularly important here, as it's a common strategy for partitioning arrays into separate categories, such as even and odd indices. Finally, always consider edge cases during testing. For instance, small arrays like 2, 1, or inputs where all numbers are duplicates can expose flaws in your logic if you're not careful. If you'd like to explore related problems to strengthen your understanding, you can look at LeetCode 905, which involves sorting an array by parity without alternating constraints. There's also LeetCode 280, Wiggle Sort, which alternates increasing and decreasing numbers, and LeetCode 75, Sort Colors, which is another classic two-pointer problem. Lastly, LeetCode 215 focuses on partitioning techniques, making it a good complement to this problem. Now let's explore some alternative approaches to solving this problem. The two-pointer technique is one of the most efficient methods. Here's how it works: you use two pointers, one for traversing even indices and another for odd indices. As you move through the array, you swap any elements that are out of place. This approach is efficient with O(n) time complexity in O(1) space, but it requires careful index management to avoid issues like infinite loops. Another option is the separate array approach. In this method, you create two temporary arrays, one for even numbers and another for odd numbers. After separating the values, you merge them back into the original array in the correct order. While this method is simpler to implement, it uses O(n) extra space, which can be a deal-breaker in interviews that require in-place solutions. Lastly, there's the brute force approach. This involves iterating through all indices and manually swapping mismatched elements by searching for the nearest correct value. While it's a straightforward way to understand the problem, it's highly inefficient with O(n) superscript 2 complexity and should only be used as a learning exercise or for very small inputs. Each approach has its trade-offs, so understanding these can help you decide the best fit for your specific constraints and requirements. Great job! In summary, we solved the problem using a two-pointer approach with linear time complexity and constant space complexity. This technique is widely applicable to similar problems. Thanks for watching, and be sure to like, share, and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!